In Hamiltonian formulation of classical mechanics, today we are going to discuss a very important concept. Actually, this concept is symmetry and conservation principles in physics, or you can say conservation principle in nature. In this lecture, or you can say this is actually the first part of the lecture on symmetry and conservation principles. So in this first part of lecture, actually we will see some introductory facts regarding the symmetry and conservation principle, and in second lecture we will actually discuss three conservation principles, that is conservation of linear momentum, angular momentum and energy in detail, which is actually the subject matter of classical mechanics. But in this introduction we will see some another conservation principle which is actually resulted from some type of symmetry. Actually, a remarkable theorem discovered by a German mathematician named M.E. Noether. This theorem actually states that every conservation principle corresponds to a symmetry in nature. It means whenever you talk about any conservation principle, definitely that conservation principle has been resulted from some type of symmetry in our nature. First of all, we have to know what do you mean by symmetry. When you say symmetry, in general, a symmetry of a particular kind exists when a certain operation leaves something unchanged. So let us take some example to clarify this definition and an introduction that how that symmetry leads to some conservation principle. So let us take first of all an example of this symmetry. You can take an example of a candle. Actually, a candle is symmetric about a vertical axis because you know it can be rotated about that axis without changing in appearance or any other feature. When you rotate the candle about a vertical axis, no feature actually changes. So we say that the rotation of this candle is symmetric about a vertical axis. In fact, it is also symmetric with respect to reflection in mirror. So this is a simple example of symmetry and symmetry operation. You also study different type of symmetry in condensed matter physics or in solid state physics. So now the simplest symmetry operation is in this space is actually the translation in space, and this translation of space actually leads to the conservation principle of linear momentum. Actually, you can say that space is symmetric in translation. What does it mean? Actually, it means that the laws of physics do not depend on where we choose the origin of our coordinate system to be. Noether showed that the invariance of the description of nature to translations in space has a consequence, the conservation of linear momentum. So you can say this principle, this symmetry, which is actually the translation is space, actually leads to the conservation principle of linear momentum. Now, in fact, another simple symmetry operation is translation in time. You can take another example. This is translation in time. Translation in time. When we say that symmetry operation is translation in time. What does it mean? It means actually that the laws of physics do not depend on when we choose t equal to 0. As you have seen that in translation of a space, it does not matter where we take the origin to measure the position coordinates. So when we say that there is a translation symmetry in time in nature, then what does it mean? It means the laws of physics do not depend on when we choose t equal to 0. It means the laws of physics do not depend when we take t equal to 0. It means this is just like origin for time coordinate. So if the laws of physics do not depend on our selection of t equal to 0, then we say that there is a translation symmetry in time in our space or in our nature. So actually this symmetry leads to the invariance principle, or you can say the conservation principle of energy. So you can say that this invariance has a consequence. This invariance has a consequence of the conservation of energy. So the symmetry of translation of a space leads to the conservation of linear momentum, and translation in time leads to the conservation of energy. Actually, invariance under rotations in space, which means that the laws of physics do not depend on the orientation of the coordinate system in which they are expressed, has a consequence, and that consequence is what? That is conservation of angular momentum. So you can say the rotation invariance under rotation in space leads to the principle of conservation of angular momentum. So invariance under rotations in space which means the laws of physics do not depend on the orientation of the coordinate system in which they are expressed. they are expressed, and this leads to what? This leads to conservation of angular momentum, conservation principle of angular momentum. Now actually we will have different conservation principle in physics, like conservation of electric charge. In fact, this principle of conservation of electric charge is related to the gauge transformation. Actually, you study this in electrodynamics, that is the gauge transformation, and you will see in electrodynamics that the conservation principle of electric charge is related to gauge transformations. In fact, in it, the shifts in the zeros of the scalar and vector electromagnetic potentials denoted by V and A actually leads to this principle. When we use the formula for the electric field vector and the magnetic field vector in terms of these potentials, then applying the gauge transformation, we find that the electric field vector and the magnetic field vector remains unaffected, and so this actually leads to the conservation principle of the electric charge. So you can say, in fact, in short, I am just giving in a written form the information which I have told you, that the gauge transformation leads to conservation of charge, Actually, what I have told you, that conservation of electric charge is actually related to gauge transformations, which are shifts in the zeros of the scalar and vector electromagnetic potentials. So what is this gauge transformation actually? Gauge transformation are shifts in zeros of the electrodynamic, or you can say electromagnetic potentials phi and A. Phi is actually a scalar electrodynamic potential and A is vector electromagnetic potential. Actually, this gauge transformation leaves the electric field vector E and the magnetic field vector B unaffected, and so that it is found that the charge conservation holds, or this invariance actually leads to the charge conservation. So you can say that this leads to the principle of charge conservation. Now we will see the another symmetry operation and the conservation principle. You know, the interchange of identical particles in a system is a type of symmetry operation which leads to the preservation of the character of the wave function of a system. And the wave function may be symmetric under such an interchange in which case the particles do not obey the exclusion principle and the system follows the Bose-Einstein statistics, or it may be anti-symmetric, in which case the particles obey the exclusion principle, that is Pauli exclusion principle, and the system follows Fermi-Dirac statistics. So the conservation of statistics, or equivalently of the wave function symmetry or anti-symmetry you can say, signify that no process occurring within an isolated system can change the statistical behavior of that system. Actually, a system exhibiting Bose-Einstein statistical behavior cannot spontaneously alter itself to exhibit Fermi-Dirac statistical behavior or vice versa. This conservation principle has applications in nuclear physics, where it is found that nuclei that contain an odd number of nucleons. When you say odd number of nucleons, it means odd mass number, which is denoted by capital A. They actually obey Fermi-Dirac statistics, while those with even mass number obey Bose-Einstein statistics. And conservation of statistics is thus further a condition of nuclear reaction. In a nuclear reaction must be observed. So you can say that the conservation principle of the interchange of identical particle in a system actually is just a symmetry operation, where we actually interchange the two identical particles, and after the change of two identical particles there may be two things. So you can say, let us consider there are two identical particles. This is particle 1 and this is particle 2. And the wave function describing the system of these two particles, let us say, is psi of 1, 2. And after the interchange of this particle, if the wave function is psi 2, 1, and this psi 1, 2 is equal to psi 2, 1, in that condition the wave function is symmetric. And if the wave function is symmetric, then you can say such a particle for which the wave function is symmetric does not obey Pauli's exclusion principle. So this implies the particles do not obey Pauli's exclusion principle. And if they do not obey Pauli's exclusion principle, you can say such particles are called bosons. And why they are called bosons? Because they obey Bose-Einstein statistics. BE statistics. statistics. But there is another class of identical particle in which case actually we find that after the interchange of the particle, the wave function actually changes its sign. So psi 12 in this case is equal to minus psi 21. And if this condition holds, then actually this represents the wave function is antisymmetric. The wave function is antisymmetric. And such particles actually obey Pauli's exclusion principle. Particles obey Pauli's exclusion principle. Pauli's exclusion principle. They obey this very principle. And as I have told you that in case of nuclear physics, this principle is variously utilized, and we know that a nucleus which have in fact even mass number, they are actually bosons and they do not follow the Pauli's exclusion principle, but the nuclei having an odd mass number follows actually the Fermi-Dirac statistics, and they are called, in fact, collectively called fermions, and their wave functions are antisymmetric. So these particles which actually follows Pauli's exclusion principle are known as fermions. And this symmetry operation is invariably used in the study of nuclear physics. Now actually more subtle and abstract than those mentioned here, which we have mentioned here, are the symmetries associated with the conservation of such quantities as baryon and lepton numbers and strangeness. Actually, these symmetries were important in the thinking that led to the current theories of elementary particles, notably the quark model of the hadrons. So you can see that this principle of symmetry is very important, even the recently developed quark model of hadrons. So you can say that this is a very remarkable fact that the symmetries associated with the conservation of quantities like baryon number, lepton number and strangeness. In fact, these quantum numbers are studied in particle physics, strangeness. So symmetry associated with conservation of quantities like baryon number, lepton number and strangeness actually leads to the elementary particle theory. Elementary particles theories, particularly the quark model. Quark model of hadrons. In fact, this example is not will be not dealt in detail in present lecture, but in this introduction I have just introduced you that the symmetry principle for the conservation of different quantities, actually it is used in various branches of physics. Even in the recently developed quark model, we use the symmetry operation or symmetry properties associated with different quantum numbers like baryon number, lepton number, strangeness, and that symmetry operation is actually utilized to understand the recently developed quark model. But actually in this topic of classical mechanics, our aim is to actually discuss only three conservation principles in very detail under the heading Hamiltonian Formulation. The first one is principle of conservation of linear momentum. The another will be principle of conservation of angular momentum, and the third will be principle of conservation of energy. But in introduction, I have just introduced some more conservation principle associated with the symmetry operation. So this is all about this introductory fact, and in second part of this lecture we will actually discuss the conservation principle of the linear momentum, angular momentum and energy from classical point of view in very detail.